Hey guys, so this is going to be the kind of demo video that I wanted you to see, kind of to explain the sun's rays hitting directly at 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 and around the equator, to kind of illustrate that the most direct rays are causing the seasons. So basically, that Earth tilt is shifting the direct rays north for our summertime and then south for our wintertime, and it's all based on position around the sun. So normally what I would do is I would give you guys tennis balls and have like a light bulb at the center of the room, and then you would kind of hold your tennis balls at different areas around the room. So basically we would kind of show you the different spots that you would hold it at. So notice that this one is the North Pole, tilts away from the sun, and so that's going to be your winter solstice in the northern hemisphere, summer solstice in the southern hemisphere. So notice I've got Denton, New York City on there just for fun, but notice that it's tilting away from the sun. Then we basically just move. Notice the square part of the block doesn't turn. We just move the Earth to the four quadrants basically, and then if we look, this is now the north and south pole are parallel to the sun, so it's the vernal equinox for us, it's the autumnal equinox for the south pole. Then again, if we rotate around one more time, now the northern pole is tilted toward the sun, so that's going to be summertime, and then the summer solstice, and then it'll be the winter solstice for the south pole. Then we rotate one more time, 90 degrees, and now we're not tilted either way towards the sun, so it's parallel again. So now we're in the autumnal equinox for us in the northern hemisphere, and then the spring equinox for the southern hemisphere. So again, that's kind of the setup, which if you notice from above, you had the 4 points again. We were away there, then parallel on the 2 opposite sides, and then facing towards it on the back side when it's the winter time. So if we know that, then this next video should help us see those direct rays. So let me pause, I'll be right back. Okay, so in this video now, it's the same block, but now I've got a little laser. You can't really see it in this picture, you might see it in a little laser beam is set up so that it's striking at the same point wherever I rotate. So I tried to get it as close to where it would be, striking as possible. In case you didn't know this, the Tropic of Capricorn and the Tropic of Cancer. So the Tropic of Cancer is up here at 23.5 degrees north latitude, and then the Tropic of Capricorn is at 23.5 degrees south latitude. What those basically represent, the axis is 23.5 degrees tilt. So when we're in that winter solstice, the sun is directly over the Tropic of Capricorn, and then when we're in the summer solstice for us, the sun is directly over the Tropic of Cancer. So it's basically like the northern equator and the southern equator in between the equator, really. We're on both sides of the equator. So the equator is like middle, where the sun is hitting during equinox, and then the 2 other ones are where the sun is directly over during summer solstices, which in the northern hemisphere, the summer solstice is in our summer, and then the southern hemisphere, the summer solstice is in our winter. So anyway, if we keep scrolling forward here, basically what I've done is I've set up this laser to strike basically over that. Since we're in the winter solstice, which is the summer solstice in the southern hemisphere, the direct rays of the sun would be striking below the equator on about that 23.5 degree latitude. So basically, if I spin the Earth, notice that it strikes directly along that line. Of course, it's a little wobbly because toothpicks and whatnot, but then if I rotate it so that it were, remember, normally the if this were the sun, the Earth would be rotating around it, right? But in my case, what I'm doing instead of rotating around is I'm just turning the face of this. So this would represent now. Notice that the axis is now not facing towards the laser or away from the laser, so it's basically parallel to the laser. And in this case, this would be the vernal equinox for us because it's going to be springtime. We just moved from winter to spring. And if we fire up that laser, notice it hits pretty close to the equator. Couldn't get it exactly right, but it's pretty close, and then it tracks along that same equatorial path, right? Then again, we'll go ahead and rotate rather than spin, right? Rotate it one more time. Now it's the summer solstice. And if we rotate, again, it's up above the Tropic of Cancer. So the most direct rays are along that 23.5 degree. And then if we rotate one more time, now we're at the autumnal equinox. And again, this is the one, and the reason I made this video is whenever it's at this side angle, to me, so what you're looking at is, if this is the sun, you know, this would be northern hemisphere in winter or in summer, and then this way over here with it still, I get that angle right for the camera, but basically the northern hemisphere would be facing away from the sun, right? So it's these middle points to me that always give me trouble, because in these middle points I feel like for some reason it shouldn't change anything, but when you put the laser beam on there, to me it makes it evident that obviously when the laser beam is or when it's the tilt is not facing it, the laser beam tracks right along the equator, which if you look back at the gizmo that we did, if that sunlight is tracking right along the equator and that's the direct rays of the sun, then that means that essentially this entire half of the globe will be well lit. So that means that for 12 hours of that 24-hour rotation around your axis, you'll have 12 hours of light, 12 hours of dark, therefore you will have an equinox. If we were to rotate that back to the summer solstice, let's say, and watch that, notice because the sun is on the Tropic of Cancer and it's in the northern hemisphere, basically from just above the pole, the North Pole, to just somewhere off of the South Pole, so towards the equator from the South Pole, will be the lit part of the globe. So that means if you're in the southern hemisphere, you won't get 12 hours of light, you'll get less because it's darker. So imagine that the lit up portion, you know, would be kind of in this area, right? And if most of the lit up portion is in the northern hemisphere, then that means you're going to get 14 to 16 hours of sunlight versus 8 down to the south, right? So to me, this kind of helps when you get to those, you know, those middle points. It helps to kind of see it. So let's look at it again. It just tracks right along the equator when you're in the equinox position. So, and again, equinox, if I didn't say it, equi is equal, and then nox is night. So it's equal day and night, or equivalent day and night, is the meaning of that word. Solstice, sol means sun, stis means too much. Just made that up. I don't know if that breaks down. I know sol is sun, but stis, stice would be. But the solstice, remember, northern hemisphere, if you're tilted toward the sun, it's the summer solstice. If you're tilted away from the sun, it would be the winter solstice. So December 21st is the winter solstice for us. It's the summer solstice for the south. Then the other thing that I need to mention, I think in the video I said that essentially in the summer days get longer and the winter days get shorter, which is something that people say because we always feel like when we are going into winter, you know, the fall, when it starts to cool down, the days start getting shorter, which is true, but really once you hit winter, the winter solstice is what starts winter. the winter solstice is the shortest day of the year. So throughout winter, your days are getting longer as you build towards summer. And so really during the winter and spring, days are getting longer. And by days, we mean daytime. And then from summer into fall, so at the summer solstice, you have your longest day. And then that's the first day of summer. Then from summer through fall, the days are getting shorter up until the winter solstice again. So figured I should correct that just in case anybody has a trivia question about it. But basically that's my kind of lame-o models. So I hope those helped. If they didn't, good luck. Basically on that quiz, what you're looking at is, rotation is what makes a day. So the Earth rotating about its axis, and then the moon rotating around, revolving around the Earth takes about 1 month. Sorry, and then the Earth revolving around the sun is a year, and then those position points for the seasons are going to be on the quiz, as well as light intensity from the Gizmo demonstration stuff. So that light intensity is kind of the same as that laser beam. When you're tilted toward the laser beam, the northern hemisphere, for example, will have more light intensity, and then when it's away, the southern has more light intensity, but the northern has less light intensity. And really that's where this whole thing is going. Energy input into the aquatic systems is going to determine what those aquatic systems look like. So we have, polar regions that are going to look terribly different from tropical regions near the equator. And all of that is going to be based on sun input, climate, and then we'll also link that into what organisms do with that energy. So really, it's kind of like, it seems like this doesn't have anything to do with it, but really it's what is the bedrock of every aquatic system that we're going to look at. So they all have something to do with Earth's placement around the sun and how it spins about its axis around the sun. So that's where we're headed. We'll get there eventually, but until then we're going to be kind of playing with celestial movement to get us in a place where, kind of like with the chemistry, we can then build onto it and put some things that kind of make sense once they hit the ecosystems. So